All right, welcome to our final video on sequences and series, which covers the idea of limiting sums. Now, a limiting sum, as you might have remembered, I mentioned it a little bit in the last video with summing up geometric series. It is a specific type of geometric series where our rate is less than 1. Now, there's a common example, you may have heard the example before, of clapping your hands together. So some people, try and mathematically explain it. You can't technically clap your hands together. If you start your hands a meter apart, there'll be a point where they're half a meter apart, a point where they're a quarter of a meter apart, and an eighth and a 16th and so on. And that will actually never reach 0. And so if you talk about clapping as being putting your hands together, you will never actually reach that point. Now, it's obviously not true because you can clap, but this is the idea that you need to be thinking about. And so what we say is that the terms and the sums converge to a limit. So a limiting sum will have a total sum that it will approach. Now, this has its own specific formula. It comes from the geometric sum formula, but I would recommend just learning this by itself, just because it's a little bit easier to learn it by itself. Now, we analyze this completely the same as we would for summing up a geometric series. As I said, it's just a specific case where we have certain things happening. All right, so the first example we have here is that a bouncy ball is dropped from a height of 8 meters. Each bounce, the ball comes back up to half the previous height. Through what distance does the ball eventually travel? So if we imagine what this ball is doing, we're throwing it off an 8 meter height, whatever that is, out a window. So what it's first going to do is it's going to drop 8 meters. If I draw up this little scenario, we've got someone throwing it off like this. It's going to drop, and this distance is 8 meters. Then what's going to happen is it's going to bounce up to 4, and it's going to come back down again, right? And so this distance is 4, and then it's going to come up to 2, and so on. But you see, it's never going to stop doing that. It's going to go 1, then a half, then a quarter, and so on. And it's never actually going to stop bouncing, technically. We're in a theoretical scenario here. So if I want to think about the total distance, well, this is going to be 8 plus 4, so 8 falling, plus 4 up, plus 4 down, plus 2 up, plus 2 down, plus 1 up, plus 1 down, and so on. What I'm going to do now is I'm going to factorize this. And I'm going to get 8 plus 2 times 4 plus 2 plus 1 plus so on. Everything, right? Now what I want to think about is inside of these brackets, I have a limiting sum because I have these things. And the way to check this, by the way, is that your rate is less than 1, because then that means that everything's going to be shrinking each time. And so I have my A equals 4 in here. I have a rate equals a half. And my n is technically infinity because I'm just thinking about infinite number of terms. So I just don't even worry about that and that's why I say to learn this formula. So the sum of infinite terms equals A over 1 minus a half, which is actually normally a really simple formula to apply. So in this case, that's 4 over 1 minus a half. That'll be a half. So 4 over half is 8. And so my total distance traveled is going to be 8 plus 2 times 8, which is 24 meters. So I say, therefore, the ball travels 24 meters. Okay, so that's the total distance traveled by that ball in each of those. All right, looking at the next one. Explain why the series 2 plus root 2 plus 1 plus so on has a limiting sum and find it. So oftentimes with questions, you'll have to actually double check that something is something that has a limiting sum. And remember, going back to what I was talking about at the start, it is a specific type of geometric series where we have the rate, the absolute value of the rate, less than 1. So that's the first thing that we want to check. We want to show that the rate is less than 1. Now, we can assume, well, looking at this, we can assume that it's a geometric progression, but I will prove also that it's a geometric progression. So if I think about my rate, well, that should be root 2 divided by 2, right? So if I have my T1, T2, T3 here, T2 over T1 is root 2 over 2. And, well, this should also be equal to 1 over root 2. Now, what you might remember from, again, the start of year 11 is rationalizing the denominator. So if I want to rationalize the denominator here, I times top and bottom by root 2. And that gets me, the top is root 2. And then the bottom becomes root 2 times root 2, which is just 2. So these things are equal. So that means that I do have a geometric progression. The other thing that I can double check, and it should be true, is that root 2 on 2 is 0.7071, so on, which is less than 1. And so I do have a geometric progression that has a limiting sum. Now to find that limiting sum, again, I just go, what's my A? My A is 2. My R, as I just showed, is root 2 on 2. And so the sum of infinite terms is A over 1 minus R, which is 2 over 1 minus root 2 on 2. And I can just chuck that in my calculator. And that gets me not a very nice number, but that will give me an approximation of 6.83 or so. I could also write this as a simplified form, if I'd like, by rationalizing this denominator, and I'll show you that. So if I want to rationalize this, first thing I'll do is times everything by 2, just to make it a little bit nicer. I'll come off here. So this will be 4 over 2 minus root 2. And then remember, when I have a binomial down here, so 2 terms, I want to times top and bottom by kind of the opposite of that binomial. So in this case, 2 plus root 2. 2 plus root 2 over 2 minus root 2 times 2 plus root 2. Right? And this is going to simplify out to 8 plus 4 root 2 over, and then that would be 4. Well, then we'd have minus 2 root 2 plus 2 root 2, which cancels out. And then we have 4 minus 2. So we're dividing by 2, and this gets us 4 plus 2 root 2. You can double check, that gets you the same answer that I got up here. Either one of those answers would be acceptable, unless the question specified otherwise. All right, the last question that we're looking at here. This is a common sort of further example that you get in this chapter. In some textbooks, it's in its own exercise. I don't think it's worth putting it in a whole separate video, so I'm including it in here. And it's expressing repeating decimals using sequences and series. So when we have 0.27 repeater, right, that's the same as writing 0.27272727, so on, right? It's going to be like that. And so I'm actually going to think about writing this as a sum so that I can express it as a fraction, right? And this is going to be 0.27 plus 0.0027, 0.000027, and so on, right? And you can double check this. If you were to enter this stuff into your calculator, you would get, I mean, each time you entered it, you would get 272727 over and over again. And so for each of these terms, now, I'm going to factor out a common rate, which will give me a rate of 1 on 100. So each time I do this, I'm dividing by 100, or timesing by 0.01, essentially. Right, and so I can write this as 0.01 times 0.27 plus 0.01 squared times 0.27, and so on. Right. The reason why I've written it like that is because this sets me up with a common rate that's applied to each of these terms. You can see it's times by 0.01 each time. So my R is 0.01, my A is 0.27. Then all that's left to do is to find the sum. By the way, this is the sum of infinity terms, which makes sense. And that's 0.27 over 1 minus 0.01, or 0.27 divided by 0.99, right? And I can simplify this to 27 over 99, or 3 on 11. And again, that can be double checked with the calculator if you need to. So that's a pretty nice trick to be able to do, in that you can convert a sort of infinitely repeating decimal just into a nice convenient fraction like we've done there.